First of all, I'd like to thank the organizing committee for the effort to hold this virtual conference and for the opportunity to present our recent work here. Today, I will give you a detailed introduction about our web-based tool ProteoPeptides for accurate prediction and visualization of proteotypic peptides in proteomics. In mass spectrometry-based shotgun proteomics, proteins are first digested by proteases into peptides, which are then taken as surrogates for subsequent analysis. However, only a limited proportion of peptides are observed or detected in a routine experiment, leading to many peptides without observations. Therefore, the prediction of proteotypic peptides, that is, detectable unique representatives of proteins, has become a crucial task. Before we talk about this study, there are two basic definitions you need to know. That is, peptide digestibility is the probability of the peptide being digested out, and peptide detectability is the probability of observing a peptide in the whole shotgun proteomics experiment. The ProteoPeptides Server can be applied to these prediction tasks for 8 commonly used proteases. So far, much effort has been made to understand the mechanisms underlying peptide detection and to predict proteotypic peptides, but the prediction accuracy of existing tools is still unsatisfactory. We found out that one crucial reason is the neglect of the significant influence of peptide digestibility. Thus, in our recent work, an advanced proteotypic peptide predictor, or AP3 for short, it has served as a significant feature for accurate peptide detectability prediction. Unfortunately, there are still very few easy-to-use tools for both digestibility and detectability prediction for various proteases. Therefore, we have extended algorithms for both digestibility and detectability prediction, and the web-based tool named ProteoPeptides, based on the 4 algorithms for 8 commonly used proteases, is presented to the community. Here, I will give you some details about the algorithms used in proteopeptides. The first one is AP3 algorithm. AP3 has 2 main components, a peptide digestibility predictor and a peptide detectability predictor. To avoid overfitting, the identified filter proteins are randomly divided into 2 halves. A random forest classifier is first trained to predict the cleavage probability of each side, which are then used to calculate the peptide digestibility. Next, all the 587 physical-chemical features of peptides are calculated. Finally, another random forest classifier is trained for peptide detectability prediction. By including peptide digestibility, the tenfold cross-validation AUC increases about 4.3% on the training dataset, and the test AUCs increase about 3% respectively. These results indicate our proposed feature, peptide digestibility, has an excellent ability in predicting peptide detectability. Another algorithm used in proteopeptide is deep digest. It's a novel sequence-based deep learning algorithm which integrates convolutional neural networks and non-short-term memory networks for protein digestion prediction. Deep digest is composed of 3 basic modules. The inputs are the 31 mirrors containing the potential cleavage size, and the cleavage probabilities of these potential cleavage size are predicted by a sigmoid function. To avoid overfitting, dropout techniques are used. Furthermore, to overcome the imbalance problem, a balanced crossing entropy loss function is used. 19 public large-scale datasets covering 8 typical proteases are used. The tenfold cross-validation and test AUCs demonstrate that deep digest has a superior generalization ability for different proteases. Subsequently, transfer learning is employed to help our model adapt to the experiment conditions, and the performance of deep digest has been much improved, especially for the 3 proteases. The last algorithm in ProteoPeptides is also based on deep learning for 8 proteases, which integrates sequence features and peptide digestibility. Since this work has not been published yet, I have to skip some details here, and welcome everyone to follow our work. Anyway, all of the 4 models are evaluated on the 19 public large-scale datasets mentioned before. For each protease, deep learning model has a higher AUC compared to random forest model, indicating an enhanced learning performance. Considering that AP3 has been published and validated by other users, we still provide the random forest models in proteopeptides. On the other hand, the unpublished algorithm needs more tests, and we hope to get more feedbacks from users. So if you have any questions about our models, please let us know. Now, let me show you how to use this web-based tool. First, you have to choose your purpose, then choose the algorithm you want to apply. Next, you need to upload your FASTA file or some specific sequences in the box below. If you just want to run some tests, you can download our sample data. Besides, users also can set a regular expression on their own. If you cannot sure how the identifier will look like with each expression, you can click Go to Set Regular Expression, then there is a test page. Before testing, you need to upload the FASTA file as well. Then select one rule and click Test. The protein headers and corresponding identifiers will be shown in the table below. After you decide which one to use, just click OK, then you will be back to the last page. Afterwards, you can choose one specific protease here to implement in cyclical digestion. In the meantime, the peptide length, the maximum number of mean cleavages should be given. Anyway, all of these parameters can just be set as default. Finally, click Run and wait a bit. The results will be popped up. The whole results will be shown in a table including protein identifiers, digested peptide sequences, and predicted probabilities in a new web page. Moreover, the results can be visualized in an intuitive way. All you need is to input the interested protein identifier in the box below the table and click Display the peptide detectability or digestibility. Then a histogram will be demonstrated in a new page. When you point to one of the bars, the corresponding sequence and predicted result will be displayed. Scroll down the page, the whole protein sequence with its digested information will be illustrated in different formats, such as FASTA, RAW, and so on. Similarly, the same information will be displayed as you point to each peptide. In addition, there is a simple introduction and a detailed tutorial in the help page, just in case you want to know more about our algorithms in proteopeptides or have any trouble using it. Finally, there is also a FAQ page, where you can check some common questions or send us your own ones. We're glad to hear any of your questions or suggestions. At last, let me sum up some take-home messages for you. We present a web-based tool named ProteoPeptides for proteotypic peptide prediction for 8 commonly used proteases, and ProteoPeptides can be freely accessed at this link. Welcome to use our tool. In the end, I'd like to thank Dr. Zhiqiang Gao for his helps in algorithm implementation, thank the Associate Professor Chen Chang and my advisor Professor Yan Fu for their supervision and all the instructions. Thank you for your attention. Any questions?